Position means at some point in time, you're somewhere. Velocity means at that same point in time, your position is changing at a rate. And acceleration means at that same point in time, your position is changing at a changing rate. What if I told you that if you knew just the function of one of those things, either position, velocity, or acceleration, you could know any and all of them? Let's find out on the boring whiteboard. Let's say there's some vehicle that starts not moving at a starting line, and over a certain amount of time it accelerates to some velocity. Here are three functions, the position, velocity, and acceleration functions, along with their graphs that describe the behavior of that vehicle during that period of time. The units of the x-axis for all three of these functions is going to be seconds after the start. Now, the y-axis, those units are going to change. But for the position function, which is what we're going to start with, it's going to be in feet from the starting line. Basically, the position function here, f of x, equals x cubed. So what that means is we can plug any x value in, any number of seconds after we started, and find what our y value is, or how many feet away from the starting line we are. Let's just say f of 2, for example. Where were we? How many feet away from the starting line were we? 2 seconds after we started moving. Well, if we draw the line up here, we guesstimate, somewhere between 5 and 10. We can put it in numerically here and calculate that, 2 cubed would be 8. So 2 seconds after we started moving, we are 8 feet away from the starting line. So f of 2 equals 8, and that would be in feet. Now, the next step up is the velocity function. But without arbitrarily knowing that, how do we go from the position function to the velocity function? The magic that lets us turn a position function into a velocity function is called taking the derivative of the position function. Now, I could spend a couple hours talking about what a derivative is and how it works, but you're going to have to do that on your own time. For now, I'm just going to tell you about all the wonderful stuff it can do. Now, when finding the derivative of a relatively simple function like this, that's basically just a variable to an exponent, all we need to do is utilize the power rule, which basically says you can rewrite your function, basically x cubed, diminish the exponent by 1, so it'll be x squared, and then multiply that variable by the old exponent as a coefficient. So 3x squared. That would be our velocity function, because the derivative of the position function is the velocity function. So voila, 3x squared is f prime of x. Really quick, every time you take the derivative of a function like f of x here, you need to add a little flying apostrophe to indicate that it's f prime of x. It's the derivative of f of x equals whatever it equals. So our y-axis has changed units. It's no longer in feet away from the starting point. It's how fast are we going at a moment. So when we ask what's happening at 2 seconds, or what's f prime of 2, what we're asking is how fast are we going at 2 seconds after we started moving? Well, we draw a line up here, we can guesstimate, or we can just plug in 2 into our new velocity function, and it will tell us how fast we're moving at 2 seconds after we started moving. So 2 squared is 4 times 3 is 12 feet per second. So the first answer was how many feet away we are, and the second answer's units are how fast are we moving away from where we started. Now, what we can do if we want to know how fast are we changing the rate of change, or how fast are we accelerating at 2 seconds, we just need to take the derivative again of f prime of x, of the velocity function, and that will tell us the acceleration function. So the derivative of our velocity function, or our acceleration function, will be 6x. F double prime of x equals 6x. The second derivative of the position function, or the derivative of the velocity function, is 6x. What's our units for the y-axis in this case? Well, it's going to be the rate of change. And that sounds really weird, but it does make sense, because when we started over here at position function, we were talking about how many feet away you were. And at the velocity function, we were saying, what is the rate of change? How quickly is your position changing? And now at acceleration, we really can just divide by that rate one more time and get feet per second, or feet per second squared. So that's our y units in this case. At 2 seconds, the acceleration function tells us that our rate is increasing at a rate of 12 feet per second or per second squared. Now, what if we wanted to go backwards, right? If we knew the acceleration function of an object, but wanted to know consecutively this way what its velocity and what its position functions were. Well, it's basically the same thing, except for just add the anti onto the derivative, and you're taking the antiderivative going this way, or the derivative going this way. When you're looking for an antiderivative, I would be lying if I didn't tell you that you do need a little bit more information than just a function, but we'll let your math teacher cover that. So what would all this crazy math look like in real life? Well, we would have to act out f of x equals x cubed. It would mean infinite acceleration, kind of like this. Just out of curiosity, what would happen if we multiplied our function by -1? Well, technically it would mean you would infinitely decelerate, but you can only decelerate until you're stopped. I was hoping to get this far into the video without too many people realizing that I was starting to introduce a few of the basic concepts of calculus. I really wish people wouldn't view calculus as some higher mathematics that I don't need and is too complicated for me. It really is so relevant. It enables us to know where something is, or how fast something is going so many seconds after it started moving, or when a ball that we just threw up will hit our head how many seconds after we threw it up. There's so many dimensions that you walk through as you take the derivative of a position function and a velocity function, and then acceleration functions, and then endless dimensions that are inconceivable to our minds, adding more rate of change to it. To me, that's simply awesome. Thanks for watching RedNeck Physics, or in this case, RedNeck Calculus.